Ethan. We're good. Take it away, Ethan Siegel.
All right. Hi, everybody. So I'm Ethan Siegel. I'm a theoretical astrophysicist. I've known Mr. Minato for about 6 or 7 years now when he first found me and said, hey, come talk at my Portland high school. And I was like, okay. And even though I don't live in Portland anymore, this online technology makes it so possible. So you may notice I have a background behind me of a gorgeous galaxy cluster, courtesy of the James Webb Space Telescope. So I decided I'd give you a talk today on the science of space telescopes and that we'd focus on the James Webb Space Telescope. So I'm going to try and share my screen. And if this works right, I'm actually going to give you a little presentation. So can everyone see my presentation here?
Yeah.
Oh, yeah, I see the thumbs up. Awesome. All right. So I want to tell you about the science of space telescopes. This is, here we go. This is not the James Webb Space Telescope. This old trash can in space, which is funny to think about it that way, is the Hubble Space Telescope that was launched way before all of you were born back in 1990, where I was in 6th grade when this thing launched, to give you an idea of how long ago we're talking about. So why would we do this? Why would we put telescopes up in space? And the answer is because of this. You look at this and you're like, oh, what a beautiful, clear night sky. But an astronomer who's interested in measuring what's out there in gory detail is going to look at this and say, this is a problem. This is no good. This image is like looking at the universe from the bottom of a swimming pool up through the swimming pool, and you get all this distorted light. Because realistically, what's happening is we are at the bottom of Earth's atmosphere. We try to overcome this, right? When we build our observatories, we don't build them here at sea level. We build them up on these mountain peaks, because, you know, Earth's atmosphere is very thick down at the bottom, but very thin up at the top. If you can get like here, above the clouds, above all of the water vapor in the atmosphere, above, you know, any sort of like turbulent airflow, if you can get cool, dry, clear, still air, you only have the upper atmosphere to contend with, and you see much better. You can imagine going even higher, like we do with, say, oh, I don't know, balloons, right? We have these balloon experiments that can take us up, way even higher up into the atmosphere. That's a good place for an observatory. But the problem is, anywhere on Earth, anywhere, even in Earth's atmosphere, you got to contend with this. From space, everything is visible. You can see gamma rays, the shortest wavelength light, X-rays, ultraviolet rays, visible light, infrared light, microwave light, radio light, all of it. From Earth, though, that's it. You can't see gamma rays, X-rays, or most of the ultraviolet spectrum. You can see a lot of visible light, but that still gets distorted. Infrared, you can see a few little windows in the infrared part of the spectrum, but most of it gets blocked. And then radio, you can see some radio waves from Earth, which we have made wonderful use of. And then that longer wavelengths is blocked again. But you go to space, you overcome all of that. This isn't to say it isn't useful to have ground-based telescopes, right? You can see some amazing stuff. And one of the big advantages of building something on the ground is you can make it big. You can change the instruments all the time. You don't have to go to space to get it and service it. So ground-based telescopes stay good and useful for a really long time because they're serviceable, because they're upgradable. In fact, this telescope, these are the twin Keck telescopes on the top of Mauna Kea. These telescopes are actually mounted together and they can perform interferometry, which means you can look at two things, like you can look at the same thing with two telescopes at the same time, and it's like your eyes, it's like having binocular vision, where you gather the light that you can see in both of your eyes, and also you can synthesize them together to kind of make a little bit of a 3D image out of it. But the biggest advantages we get come from going to space. You go to space, and now there's no atmosphere above you. What your telescope can see optically, right, which is just what's your telescope's resolution? It's the number of wavelengths of light that can fit across your primary mirror. And that's it. You build a perfect mirror, and you look up at what you can see, and you can see incredible details that you could never, ever, ever see from Earth with having to contend with the atmosphere. So here's an example of a telescope's, like Hubble's, view of a spiral galaxy. And holy crap, like how amazing is this? You look at this and a bunch of features should jump right out at you. You can see, first off, that this is a face-on spiral galaxy. You can see that there's bright, bright spiral arms going around it, right? Traced out in blue. Those little blue dots, those are hot young stars that trace the spiral arms of the galaxy. You will also see those dark lanes. That is dust. That's neutral matter. That dust is going to gravitationally collapse and give rise to new stars. And you see those pink features? Well, those of you who've had a chemistry class will remember, oh yeah, atoms, right? Atoms are out there in the universe, and every atom has a nucleus and electrons that go around it. And if you hit one of these atoms with just the right wavelength of light, it'll catch that light, absorb it, and the electron will jump up in energy levels. Also, the opposite happens. Excited electrons drop down in energy levels, and they emit light of a very specific wavelength when they do that. Those little red and pink regions you see dotting the spiral arms of these galaxies, those are singly ionized hydrogen atoms that have their electrons recombining with the nucleus and dropping down in energy levels. When you drop from the third energy level to the second energy level, you emit this specific red photons of 656.3 nanometers. So when you see a picture of a galaxy and you see those pink regions around it, those are star-forming regions, and that's ionized hydrogen you see in them. And you can see it like just in your own visible light images from a space telescope. You can also say, hey, what about some wild things that we can see? Well, how about this? This is the Cartwheel Galaxy, and you can see two other galactic neighbors on it. The quiet looking one, the one that doesn't have any blue stuff on it, that's just a background galaxy, not doing much of anything. The other two, though, what happened was the galaxy you see on the left, that one has crashed through the center of the galaxy known as the Cartwheel Galaxy and expelled gas in a giant ring. And that ring has formed new blue stars all throughout it. We don't expect this feature is going to last very long, but it's here now while we're looking at it, which is pretty amazing. One of the things I love, though, about going to space, I want you to remember we said you can see visible light down here on Earth, but most of infrared light you can't see. I want you to look at two images of the same object. One image is in visible light, the other image is in infrared light. What do you think? On the left, visible light. On the right, infrared light.
Wow.
This is a dark nebula. This is a gas and dust cloud. This specific one is called a Bok globule. Its name is Barnard 68. And what is it? It's just a cloud of gas. But in infrared light, right, it blocks visible light, but infrared light is longer wavelengths. All throughout the universe, dust, light blocking material, it's made of grains of a specific size. If your wavelength of light is small compared to those grains are going to interact with it and absorb it. If your wavelength is long compared to those grains, it'll just pass right through. It won't absorb it. So that's why we like to look at the universe in longer wavelengths of light, because in short wavelengths of light, lots of that light gets blocked. But in long wavelengths of light, we can see through the light blocking stuff and can talk about the universe beyond that. So you can't see the background stars behind the stars in visible light, but you can in infrared light. And this is going to be important in a little bit. So I want to show you, they had an idea after the Hubble Space Telescope had been up for about 3-4 years. They said, you know what I want to do? I want to take a look at this region of sky. Why this region of sky? Because there's nothing there. That little L-shaped region, only a few faint stars, no known galaxies, nothing. We didn't know of anything that was out there. And so they said, what I want to do is I want to point my Hubble Space Telescope at this region of sky, and I want to look at it for minutes and hours and days on end. And I just want to look and look and look and see what shows up. And a bunch of people said, oh my God, don't do this. This observing time is so valuable and you're not going to see anything and you're just going to waste it. And the director said, no, I think this is important. Let's do it. And what came back was this. This was our first deep field view of the universe. And what we found were, oh my God, it's full of galaxies, thousands and thousands of galaxies in this little region of space that we found. And when we analyzed the galaxies that we found that some of them were close by, some of them were very far away, and some of them were very, very, very far away. In fact, when you break it up, we found that there were galaxies. Yeah, there were a few that were nearby that were only like 5 billion light years away or less. And then there were a lot more that were an intermediate distance away, that were like 5 to 9 billion years. That's how long it took for the light to reach us. But even beyond that, we found there were galaxies 9, 10, 11, 12, even 13 billion years. That's how long it took the light to reach us in the expanding universe. But we also started to see, ooh, we're not seeing as many ultra-distant galaxies as we thought we would, which was a hint to us what we probably need is a telescope that's more sensitive than Hubble for finding these things. Because Hubble's great, but Hubble has a few disadvantages to it. Number one, Hubble's small. It's only about 2.4 meters in diameter, which is big for, you know, a human, right? You're 2.4 meters tall, you'll be dunking on Shaq all day. But, you know, for a space telescope, we'd love that, but we have 10-meter telescopes on Earth, and we're working on building 30-meter telescopes here on Earth. 2.4 meters sounds pretty rinky-dink to me. Another limitation of Hubble, Hubble is warm. Hubble, even though it's, you know, looks like it's wrapped in aluminum foil, Hubble is in direct sunlight in low Earth orbit. It can't get all that cold. And as I'm sure you know, every time you accidentally touch like a frying pan or a fireplace or something, you know, that's hot but doesn't look hot, like it's not glowing, hot things don't look hot because hot things don't radiate visible light, they radiate infrared light. So Hubble can't see very far into the infrared because it's at a high temperature. If you could cool it down, it could see farther. And also Hubble has, you know, old instruments on it. The newest Hubble instruments were installed in 2009, and it's never going to get any newer instruments than that. But that said, Hubble gave us, until the James Webb Space Telescope launched, our deepest view ever of the universe. This little box that I've got outlined that says XDF is the Hubble Extreme Deep Field. with Hubble's eyes, it was able to identify 5,500 galaxies in this tiny little square of space.
Wow.
But what was amazing about this is it saw this tiny little 5,500 galaxies in an area of space that was just 132 millionth of the whole sky. So if you said, okay, Hubble, you see 5,500 galaxies in a region that's 132 millionth of the sky, how much would Hubble see if it could see the whole sky at once? And the answer is 170 billion galaxies. As it turns out, that's only about 1% of our estimate for how many galaxies there are in the whole universe. Because Hubble is limited, it can only see the brightest, closest, most prominent galaxies. But James Webb is taking us beyond those limits. The JWST, its first and arguably most famous image is this. And immediately, we know it's seeing things that Hubble could not see. JWST has been doing science operations for about 6 months now. And in that time, it's already broken Hubble's record for most distant galaxy we've ever seen. If you ask, what are the 10 most distant galaxies we've ever seen? 8 of them were found by the James Webb Space Telescope. And like, its science results just keep pouring in, and its images are nothing short of spectacular. So what is James Webb Space Telescope? Well, one thing it has over Hubble is it's a segmented mirror. It's made out of 18 hexagonal segments that are tiled together. Why? So it could fold up and fit in the launch vehicle and then unfold and still have that incredible light gathering power. The gaps between the segments in a deployed James Webb Space Telescope are only 4 millimeters. But if you were to draw a perfect parabola across these 18 segments, you would find the 18 segments line up to within 20 nanometers of that perfect mathematical surface, which is incredible. Best ever of all time. This is one of James Webb Space Telescope's instrument. This is the NIRCam instrument. This is when you see a James Webb Space Telescope picture, it's probably taken with this instrument. Light goes in, right, gets reflected off the primary mirrors, off the secondary mirror, into the instrument's focus, right into this thing. And then what happens? It says, okay, we're going to look at it and see what wavelength of light is this, and how much energy does it have, and how bright is it, and where did it hit? And bam, add those photons up and you make a space telescope image. There's also a mid-infrared, right? Near-infrared is relatively short wavelength light. James Webb Space Telescope has that 5-layer sun shield on it to shield the space telescope's assembly from the sun. So the hot side is daytime temperatures, but the cold side is about 40 Kelvin. So James Webb Space Telescope can take you from direct sunlight to 40 Kelvin with 5 layers. And that's great for near infrared imaging. That's cold enough. But if you want to go colder, like past about 5 microns in wavelength, human eyes can see from 0.4 to 0.7 microns. Near infrared is about 0.7 microns to 5 microns. James Webb Space Telescope, though, has an instrument that can see from 5 microns up to about 28 to 30 microns. And for that, it has a mid-infrared instrument. And guess what? You see all that extra crap on there? That's a cryocooler. James Webb Space Telescope uses liquid helium to cool itself down to 6 Kelvin. So that one instrument is kept colder than the rest of the observatory, so it can see even longer wavelengths of light. And that's great for viewing not just like infrared, like, okay, longer wavelength stuff. Mid-infrared is special for seeing dust, for seeing star-forming material directly. And that's pretty amazing. This is what a fully assembled James Webb Space Telescope primary mirror looks like. that got attached to this apparatus. That big thing is the ISIM module. That's the Integrated Science Instrument module. It has all 4 of the main science instruments. And this is what a fully deployed primary mirror looked like just before they went and put it into final testing to ship it off, to fold it up and ship it off to where it went into this Ariane 5 rocket. I don't know how many of you stayed up December 25th, Christmas morning, got up at like 4 a.m. in 2021 to watch this launch. But I did, and it was a very emotional thing for me because I knew that this launch is going to determine everything for this telescope. If the launch is a success, they were predicting 5.5 to 10 years of science lifetime for the James Webb Space Telescope. The launch was so perfect that the solar panels came out early, and when all was said and done, they realized they weren't going to have 5.5 to 10 years of science operations with James Webb Space Telescope. They were going to have about 22 to 23. So this telescope should still be operating by the end of 2044 with how good that launch was. So first image that came back, least impressive thing you'll see, maybe. This. Wow, way to go, James Webb Space Telescope. What did you see? What's amazing about this is the same star as seen individually by all 18 of the mirrors. When they did that, they said, oh, check this out. I know what I'm seeing. Here are the different segments that this corresponds to. So now that we've found all the segments and all the images, let's align the telescope. So, okay, they went and said, okay, we're going to properly align this. Next image was this. Oh, wow. And then they said, okay, well, now we've got 18 individual images on each of the individual segments. Let's stack them together to make one completed image. And they did. And this is that image. Now you look at this and you're like, hey, why isn't this just a point? A star should be a point. No, this is pretty perfect. The reason this is perfect is because James Webb Space Telescope is not a perfect circle. It's not a perfect hexagon either. It's a series of tiled hexagons with gaps and support structures that hold the secondary mirror out in front of it. So all of these make optical imperfections, and that's why James Webb Space Telescope's final image of stars has that spiky pattern to it. In fact, astronomers gave this a name that I still call it by, even though they're trying not to call it anymore. They called this the nightmare snowflake because it was such a complicated shape. But you take a look at this and you say, hey, so after like we looked at this and saw aligned segments, okay, so now when we look at a real star, what do we see? And the answer was this. Yeah, you have those spikes, sure, but look at that. Even in the glare of these spikes, you can see the sharp features of background galaxies shining through behind even this bright star. So then it got people wondering, okay, so if it starts looking at things we've already seen, and it looks in its own infrared light with its own incredible optics, what does the James Webb Space Telescope see? So you remember this face-on spiral galaxy? The James Webb Space Telescope looked at it with its near-infrared eyes. This is optical. This is near-infrared. Whoa. So all of those dusty features that just look like dark lanes here, you can see them popping out. This is warm dust that's radiating in the infrared. At even longer wavelengths, you go, I wonder what this looks like in the mid-infrared. And guess what? Holy crap. Incredible. In fact, the thing I noticed the most is all of that obscured stuff Look at all this junk in the middle region here. Look at how it just disappears in the mid-infrared. You can see through different things. By looking in different wavelengths of light, you can highlight different features, which is incredible. Remember, we looked at the Cartwheel galaxy earlier. Well, here's the Cartwheel galaxy as seen by the James Webb Space Telescope. Pretty incredible. In fact, they made a composite image. And that's what that looks like. Look at the difference between the James Webb Space Telescope image and the Hubble image. Look at how many more background features there are in the James Webb Space Telescope image. There is so much more detail here. That's one of the key things, is that when you are looking in new wavelengths of light, and specifically at longer wavelengths of light, you're able to see farther and deeper into the universe. The James Webb Space Telescope is also a significantly bigger telescope than Hubble. It is 6.5 meters in diameter, so it has about 7 times the light gathering power as Hubble. You might have also seen, there was a thing called the cosmic cliffs. Hubble Space Telescope's view is at the top. James Webb Space Telescope's near-infrared camera in the middle, and the mid-infrared camera on the bottom. One of the things that I was excited for was the James Webb Space Telescope took a look at the planet Jupiter. And wow, what was it able to see? If you haven't seen this before, I want you to focus on a few things. The great red spot looks amazing. Those bluish things at the top and bottom of Jupiter, at like the ice caps, those aren't ice caps. Those are auroras on Jupiter. Jupiter has constant ultraviolet and infrared auroras that it emits around both poles. Look at that ring around Jupiter. You've heard Jupiter has rings. How incredible that the James Webb Space Telescope can see it. That big moon to the left of Jupiter, that's Io. And no joke, look above and below on the left. Can you see those faint smudges that are there? Those are actually background galaxies. As bright as Jupiter is, James Webb's optics are so good, it can even see background galaxies when it's imaging objects in our own solar system, which is some pretty incredible stuff. James Webb Space Telescope took a look into a galaxy, and this is what a different spiral galaxy looks like to the James Webb Space Telescope. You can see just tremendous amounts of star-forming material littering the arms. Do you see that there's like a spiky pattern at the center of the galaxy? When it looks in mid-infrared light, some galaxies that we see have active supermassive black holes, and they're not emitting optical light and they're not emitting near infrared light. But when you look in the mid infrared light, some galaxies shine so bright that they make that spiky pattern. This is not an example of one of those. That spike is a star in our own Milky Way, but the other stars you see, that is the largest star cluster in the local group. It's actually in a satellite galaxy of the Milky Way called the Large Magellanic Cloud, about 165,000 light years away. And this star cluster, I'm going to give you the full resolution version, actually contains the single most massive star known to humanity. The star is named R136A1, and it weighs in at 260 times the mass of the sun. And it is the bright star at the center of this cluster. One of the big advantages you get from seeing these wavelengths that no other observatory has seen at these resolutions is you can look in a star-forming region like this and say, hey, look what we can trace out. We can trace out where's atomic hydrogen, just pure H atoms. Where's molecular hydrogen? You know, hydrogen, H2 molecule. You can see that too. What about hydrocarbon dust? Things with carbon and hydrogen bound together. You can tease that out also. And you see, even though they're in kind of the same regions, their distributions are totally different. This is part of the power of having an observatory that can do infrared spectroscopy, is you can see what are the different elements, what are the different molecules, what are the different signatures, and where are they? We can literally make maps of what is where anywhere in the universe we look. One of the things James Webb was able to do was directly image exoplanets. Here's its first one. You see that bright star in the top image? Well, that star is where the little star symbol is in each of the images below. But the James Webb Space Telescope has a coronagraph, this little disc. It just comes out and it blocks the star itself, and it allows the telescope to see what's nearby that star. And guess what? This is the James Webb Space Telescope's first planet that it saw. Left two images are taken with two different near infrared camera filters. The right two images taken with two different mid-infrared filters. We can see what this planet is like, and from getting its light in different filters, we can even determine the planet's temperature. There's also this idea of, hey, every once in a while, when we're looking at a star, a planet will pass in front of that star and do what we call a transit. And when it does, it not only blocks a part of that light, some of the star's light filters through the planet's atmosphere, if it has one. So we said, hey, if we could take a spectrum of that, we could find out what's in this. And guess what? This was one of the first things the James Webb Space Telescope did. It said, hey, I know of a system where you've got a hot exoplanet transiting in front of its star. Guess what? We were able to detect carbon dioxide in this because it blocked different colors differently. And that said, hey, check that out, carbon dioxide. Another thing that it can do, and maybe my favorite thing that it can do, because I'm a cosmology guy, I love large-scale structure of the universe and how galaxies assemble across cosmic time, is it has done these surveys, deep surveys of the distant universe, and it found all of these young galaxies. Even though these galaxies are only 1 to 2 billion years old in this image, we see that they still have advanced structures, right? Some of these galaxies are very massive. Some of these galaxies are intrinsically very blue. Some of them are rather red. Some of them still already have spiral structures in them. If the Hubble Space Telescope showed us what the universe looks like, the James Webb Space Telescope is teaching us what and how did the universe grow up. We're also capable of seeing protoplanetary disks around very young stars. They have these disks of gas and dust that get gaps in them where the first giant planets form. And we're actually able to see the gaps in these disks. That's evidence of planet formation. I want to show you how we know that James Webb is so much better than Hubble was. This is one of Hubble's most iconic images in visible light on the left and in infrared light on the right. These are the pillars of creation in the Eagle Nebula. You can see these are big gaseous structures where new stars are being born inside of them, but from outside of them, adjacent stars are working to boil that gas away. Well, James Webb Space Telescope, here's what it sees. In near infrared light, you can see so much more detail than you can in the Hubble image, as well as so many more background stars and such detailed features. But here's what it sees in the mid-infrared. You really get a close-up view of those dusty structures and see just how phantasmal it all is. I'm really pleased to report to all of you, even though you're all still in high school, this telescope, this observatory will still be operating all through your teen years, through your 20s, and into your late 30s. And if we don't have something that can go out 1.5 million kilometers from Earth and service it by then, I'm going to blame every one of you for not inventing it. All right. And I think because that's about, that brings us to about 7:45. I think I want to stop here so we can spend some time having a nice discussion and Q&A with you folks. And if I can figure out how to stop sharing my screen, I will.
Thank you very much.
Yes, thank you, Ethan. That was great. So students, there was a lot of information there. I challenge each of you to have at least one question. Just turn on your mic and introduce yourself and state your question, or you can always put it in the chat.
Yeah, if you put it in the chat, I'll read it. If you want to say it, just, you know, this is Zoom. You know how Zoom works.
They're pretty good at Zoom.
You talked a bit at the beginning about there are lots of benefits to looking in longer wavelengths of light because it can get through dust and other stuff. Are there any benefits to looking in shorter wavelengths of light? Sure,
There's many. My favorite is, you know, first off, when you talk about objects in the universe, the high energy objects emit short wavelength light. The low energy objects emit long wavelength light. So if I say, okay, I'm really interested in things that go boom, like stellar cataclysms, I want a gamma ray observatory. I want an X-ray observatory. If I'm interested in what's going on around black holes and what are they accelerating and putting out, yeah, give me those. The biggest advantage, though, to going with a short wavelength observatory is, remember what I told you about resolution. You have a mirror and your resolution is the number of wavelengths that fit across that mirror. So if you have a very short wavelength thing, you can fit a lot more wavelengths across your mirror than a much longer wavelength thing. So even though the James Webb Space Telescope is 6.5 meters compared to Hubble's 2.4 meters. Hubble has an instrument that can see ultraviolet light, and James Webb does not. The shortest wavelength James Webb Space Telescope can see is about 550, 600 nanometers, which is like yellow light to human eyes. Hubble can see wavelengths of light that are like 100 nanometers. So Hubble can see much shorter wavelengths of light, and at its ultraviolet limit, Hubble can still get better resolution than the James Webb Space Telescope has. So biggest advantage in terms of wavelength, short wavelength is better resolution, but longer wavelength has its own set of advantages, including we can actually get better images. You remember a few years ago, we got the first image of a black hole's event horizon? That was taken with radio data, because even though it was just a series of radio telescopes, they were distributed all over the world. And there's a trick you can use with a series, an array of telescopes called very long baseline interferometry. And if you can know to a precise enough time how to make, okay, the light is coming from a distant object and it's arriving at this telescope and this telescope and this one and that one, it arrives at all the telescopes. If you can sync them up, like with atomic clocks, then you can say, okay, I know what is simultaneous to all of these telescopes. And therefore you can have like a virtual telescope that has the light gathering power of all the individual dishes added together, but the resolution of the space between the dishes. So you can actually treat this radio network of telescopes like a telescope with 10,000 to 12,000 kilometers to get resolution. And that's how we can actually see the black hole. So short wavelength and long wavelength both have their advantages, and different astronomers will try and convince you that their wavelengths are the best.
Of course. Of course.
I did have one question. At the beginning, you mentioned, I think it was the second book that you mentioned. You said that where each page is what you said, 100 million years, or how many?
100 million years.
Yeah.
So our universe is 13.8 billion years since the Big Bang. So 100 million years is 0.1 billion years. So, that tells you I've got about 140 separate chapters to write if I'm going to start before the Big Bang and come all the way up to the present day. But good news, I've already created the sun and the earth. I've gone from before the Big Bang to 9.8 billion years after the Big Bang. And if I've made it that far, it's only 4 billion years till the finish line. I'm going to get there.
And so the thing that I was wanted to say is that it reminds me a lot of both, because you said the name of it, and it reminds me a lot of like the cosmological calendar, and then also like the foundation with, do you know, was it referencing, because you said it was the encyclopedia?
Well, we're calling it the Encyclopedia Cosmologica.
Yeah.
Because back in the day, first it was Isaac Asimov who had the imaginations of an Encyclopedia Galactica, but Carl Sagan included it in his original 1980 TV series Cosmos. And I told you I got some famous space artists to do it. One of the two space artists doing it, his name is John Lomberg, and he was the art director for Carl Sagan's original Cosmos. He's in his 70s, he lives in Hawaii, and he's doing about half the illustrations for this book.
Wow, that's really cool. Yeah, thank you.
Any students, any other students? Yeah. There's one there from Isaac in the chat. Ethan, can you see it?
Oh, yeah. I said that it's expected JWST will last until around 2044. Do you think the next space telescope might have a longer? You have to do important things like turn and point at an object. You want to be able to point at something, you have to spend fuel to do it. So Hubble has this problem. James Webb Space Telescope has this problem. It'll keep operating until it doesn't have any oomph. Also, James Webb Space Telescope is orbiting. So you have the Earth, you have the moon, and then 1.5 million kilometers away from the sun, you have this point. It's called the L2 Lagrange point. It's great because this is where the forces from the sun and the earth add up, so that you have the sun way over here, the earth is here, and the L2 Lagrange point is here. This point always co-orbits with Earth. So Earth takes 365 days to go around the sun, and the L2 point goes along with Earth exactly the same way. The problem is you can't make a stable orbit around this. You have to keep burning fuel a little bit at a time to stay at the same place. So there is a refueling port on the James Webb Space Telescope. And if it dies and it runs out of fuel and we send something up there, we don't have the capabilities now, but like 3 different space companies are talking about, we want to build servicing to the L2 Lagrange point. Like I said, I'm going to blame all of you guys if I'm an old man and you don't have this. So make it happen, right? I expect that the James Webb Space Telescope will last then. But for example, the next NASA flagship mission after the James Webb Space Telescope is going to be called the Nancy Roman Observatory. That one's going to L2 also. But the one after that has just been named the Habitable Worlds Observatory. And that one is going to be like a James Webb Space Telescope sized observatory, but it's going to be focused in optical wavelengths. And its goal will be to take the first direct images of Earth-sized planets around sun-like stars. And in order to get that observatory up there, they are saying we need to have the capabilities to robotically service observatories at that point 1.5 million kilometers away from Earth. So I think if we're talking, okay, Nancy Roman Observatory, that's the one for this decade. Habitable Worlds Observatory will be launching in the 2030s. If we don't have servicing at the L2 Lagrange point by the end of the 2030s, we didn't develop our technology right. So, you know, you'll never build something that'll last forever because everything costs fuel. But if you can keep servicing it and keep refueling it, yeah, you can live a lot longer. In fact, many of today's observatories, on the ground at least, they've been up there, they've been operating for a really, really, really long time. The biggest advances in the last 30 years of astronomy hasn't come from building telescopes bigger and bigger and bigger. It's come because we've gotten more efficient. We have better instruments. We make the most of our photons. We have better camera technology, better CCD technology, better light throughput, right? All of these technological advances, they're not as impressive as, hey, I built a bigger thing, but more efficient is also better. It's not just bigger is better.
Harrison, I think you started to ask a question. Was that?
Yeah.
Go ahead.
So I remember you mentioned that the Hubble Space Telescope looked at some galaxies that were like around 12 to 13 billion light years away. And I remember you mentioned that the universe is around like 14 billion years old. So I imagine that those galaxies that you're viewing that are so far away are going to be like very early kind of proto-galaxies. Would there be a limit to how far we would be able to see back? And are we going to get to that limit soonish?
Yes. The answer to the first question is yes. And the answer to the second question is, oh God, I hope so. Because look, the universe, born in the hot Big Bang, it was very uniform. We fully expect that in the early universe, there were no stars, there were no galaxies. It took a really long time for these initial imperfections, these tiny, tiny overdense regions, which are like 0.003% denser than average, to actually grow from these little seeds, attracting the matter from around them and accumulating all of this matter from the average and lower than average density regions. It took a really long time for them to build up and actually form the first stars in the universe. One of the hopes is that the James Webb Space Telescope will be able to detect light from stars that are forming from pristine gas from the Big Bang for the very first time. The oldest galaxy that Hubble ever saw came from only 407 million years after the Big Bang, but that galaxy was super bright. In order for us to be able to see it with Hubble's limited capabilities, it had to be like super, super big and bright for that early time. The James Webb Space Telescope has already seen 4 galaxies that are earlier than that are from 300 and something million years after the Big Bang. I expect that when all is said and done, James Webb Space Telescope will deliver us galaxies as early as 200 to 250 million years after the Big Bang. That's my hunch. But there may be stars that formed even earlier, as early as maybe just 100 million years after the Big Bang. And for that, there's a reason that we're never sated with what we've discovered, because we want to know it all. And we know that whatever's out there beyond the current frontier, we haven't seen it yet. Does that mean there's nothing else to see? It could be. We could have seen it all and we don't know. But it's very likely that, there's plenty of more stuff, because we should be able to see all these different stages of assembly. And even now, the earliest things that we're seeing, they're clearly evolved. They've been around for a little while. So we will hit a limit someday. James Webb's going to bring us closer than Hubble ever did, but we're not there yet.
That's really cool. Thank you.
Yeah, it's a good question.
Thank you, Ethan. Several times you referred to the students saying, if you don't have this figured out, I'm blaming your generation. So as a last question, any advice to 16, 17, 18, 15-year-olds who came to this talk or who watch it recorded later, who are interested in engineering, astrophysics, maybe even art? You referred to artists. Any advice to the students listening?
I would say you have to recognize it takes all kinds of people with all kinds of talents and toolkits to contribute to this. The universe, astronomy, space, whatever it is you love about existence and you want to know more about, this is for you. this is your universe just as much as it's anyone else's. And when you bring your unique talents, your unique toolkit, your unique, some of your experiences that you've collected, know that you can contribute to this field. So if this is something you're passionate about, you're going to have skills and talents that you bring to the table, and the rest, the stuff where you're like, oh, I'm not good at that, that's my weakness, you can learn that, you can develop that skill. So if this is something you're excited about, if there is something you're excited about and you want to contribute to it, know that you can. Part of it's going to be getting lucky, part of it is hard work, part of it is finding the right support network for yourself, but you can absolutely do this. I don't want you to look at me and be like, oh, that's Ethan, I could never be like him. You think I wasn't a high school student who didn't know what he wanted to do at some point? You think I didn't go to college, graduate, and get a job as a high school teacher because I didn't know what I wanted to do next? Then I went back to grad school. Then when I was in grad school after that, I was a research scientist, and I was like, oh, I don't love this. What do I do next? And the answer turned out to be, oh, I'm going to invent this job for myself where I'm an astrophysicist who writes about astrophysics for a living on the internet. And guess what? 15 years later, it's my full-time job, a job that didn't exist when I was in high school, college, or grad school. So, you know, anything that you're like, I'm interested in doing this, pursue it. If you go through life and you're like, I won't be able to live with myself if I don't learn this thing, or I love this thing so much, I want to keep doing it for as long as someone will let me do it, keep doing it. Because whatever it is that you'll be doing down the line, that might not even exist yet. Don't worry about it. You're at a stage in your life where you're curious, you're full of, I want to know this. Get out there and learn it. You can make it happen.
All right, that was very inspirational. Thank you, Ethan. Students, if you're willing to turn on your camera and at least turn off your mute and give a little applause for Ethan. He took
You
many
can
hours
stop
out of his
recording
life
if you don't want to
create
see him.
this presentation and an hour delivering it. As always, Ethan, it was fabulous. We appreciate it. And we'll talk to you next year.
Yeah, well, thanks so much for having me, and all the best to you. Good luck.
So long.
Thank you.
Goodbye,
Bye.
everyone. Good night. Thanks for coming.
Bye.
That talk was wild.
Yeah, he's an amazing speaker, isn't he?
Yeah,
Stop
I
the
think
recording.